Ready?
Did we put any of that in? I think no.
I think all of that is garbage. Hi, my name is Linnea.
I'm Bezia.
And I'm Linnea, and this is episode number 12 of the Lemma Journal Club.
What is the Lemma Journal Club?
The Lemma Journal Club is the show where we read every paper to tell you if you need to read it. You probably do.
We have a terrific paper for you today. We are talking about the research paper, Quantum Imaging of Biological Organisms Through Spatial and Polarization Entanglement. Is that right? Yes. Okay.
Off to a great start.
By Yide Zhang, Zhe He, Xin Tong, David Garrett, Rui Ca, and Lihong Wang.
Okay, so Bez, why did you pick this paper?
No, I have to say it was in Science Advances, and it was published March 2024. Do you think HHMI would be angry at our format because we specifically say the journal and the year? Or I guess they don't care about the year, but because we say the journal?
I think that this would be like if we were funded by if this podcast were funded by HHMI, they would ask us to remove.
HHMI, if you provide funding for this podcast to get us a better audio solution in which we can look at our monitors at the same time as recording audio, we will stop saying journal names. No, I don't think we would take their money for this. I think that would make things too complicated. I picked this paper. You asked, why did I pick this paper? I picked this paper. Geez, I don't actually remember. So like a few years ago, we read a paper about quantum entangled photons to image better than the diffraction limit. And the trick there was, let's say that you're imaging with 400 nanometer photons, then you can't really image anything significantly better than 400 nanometers. There's lots of asterisks to that statement, and people are like, oh, the lambda over 2. Anyways, it doesn't matter. You could use smaller photons. You could use a 50 nanometer photon, but then the photon becomes super energetic and super damaging. So we read a paper that somehow used quantum entanglement, where it sent out 2 photons that were 400 nanometers, but somehow behaved as a 200 nanometer photon.
So this is what I was reading about right before you dragged me in here to start the podcast, which is, you create a biphoton.
Create a biphoton.
Which is when you take this high energy photon and it becomes 2 photons somehow.
Okay.
And that this biphoton has an energy of 2e, which means that it's a single quantum unit entity, and it has an energy of 2e, which means that it has a wavelength of lambda over 2.
Okay. And then you split the biphoton and you only hit the sample with the half a photon, so it's actually lower energy, but you get the imaging quality of the biphoton.
Yeah.
And we read this paper a few years ago, and we talked about it during our car ride for hours, and we could not wrap our head around this paper. This week, I decided I wanted to look more into these kinds of imaging techniques, these quantum mechanical imaging techniques. I think that this will be a lot of fun for a lot of people to listen to. Don't give up just because it has the word quantum in it. I'm glad that you looked up the thing about the biphoton. What this paper is, and I've done this wrong twice now. We did the paper on volumetric imaging of 3D orientation with a polarized fluorescence light sheet microscope by Talon and Rudolph and many other people. There, I had a lot of difficulty wrapping my mind around the concept that that technique only works for fluorescence microscopy.
Yeah.
Because I normally think of polarization microscopy techniques as a bright field technique. Here, I did the opposite mess up, where I had a lot of difficulty in this paper wrapping my head around that this was not for fluorescence microscopy.
This is label-free.
This is a label-free bright field technique. This is a quantum bright field technique, essentially. And I didn't understand that until quite late in the game of trying to understand what's going on. But this is by the same group, or at least the same last author, as the group that brought us the biphoton paper. So here it's a different trick, right? And we learned a lot about a lot of cool tricks here, such as squeezed photons.
Yeah.
So I just want to talk for a second about squeezed light. Normally, this podcast is just me talking directly to Linnea. I unfortunately was so excited about this paper that I had to talk to Linnea about it before we were actually recording. I talked to her about it like a day or two ago. And the conversation was about the idea of squeezed light, which is just such a beautiful name. And so squeezed light is something that they just say in passing, like, here's a quantum mechanical technique that's kind of useful, where it says, hey, normally when you have some flux of light, some number of photons that are coming in and you're counting them, you have a very strict rule of the number of photons that you have, the square root of that number is the noise on your reading. So if you have 100 photons, that is your signal, then the square root of 100 is 10. So it's 100 plus or minus 10 is what you're going to get for photon counts for each pixel. And they say, look, that's like a fundamental rule of the universe, that the Heisenberg uncertainty principle actually prescribes that rule. And it prescribes that rule because there's many ways to write the Heisenberg uncertainty principle. You can have, that the energy and time have restrictions, or that the momentum and position have restrictions. But one way to write the Heisenberg uncertainty principle is that the photon flux, the uncertainty in photon flux and the uncertainty in polarization have to obey the Heisenberg principle. And that leads you to this square root rule. So they have a trick that they have that I think is really beautiful, where they say, we're going to take the photons and we're going to make them incredibly uncertain in polarization, because we don't give a shit about polarization. We just care about how many photons we got. And so that's going to remove the square root rule. So if you're incredibly uncertain about the polarization of your photons, you can become incredibly certain about the number of photons. And that's called squeezing light, which I think is a beautiful idea. That's a way to make a microscope through quantum mechanics that has incredibly little noise, because you've cheated the rules of physics a little bit.
So is this an explanation? So we talked about squeezed photons earlier this week, and I was like, enamored with this explanation that you gave. And then I came to read the paper because I hadn't read it at all at that point.
It has nothing to do with the paper.
Has nothing to do with the paper. But this SSN that they refer to. Is this how they get this sub-shot noise, or is this unrelated?
Sub-shot noise means that you're beating this square root n.
Okay.
I'm not quite sure that they actually do get sub-shot noise.
Well, they do care about polarization, at least towards the end of this paper.
So they never say in the paper that, well, they do say they use a sub-shot noise algorithm to achieve higher signal-to-noise ratio. I don't know if they beat out this square root of n, but the way that they're cheating the noise a little bit, they have a different cheat, which is if you look at figure 1, they have their beam path, and they have their signal beam, which is the they create 2 entangled photons through a crystal. One photon goes to the sample. That's called the signal beam. The other photon, Linnea already knows all this. I'm just putting this out there for the audience, because the audience really is not going to want this one.
I think it's a good educational paper.
One photon is going to the sample. That's the signal beam. The other photon is going off to do some quantum mechanics nonsense. That's the idler beam. Okay, and they use.
I love that term,
idler beam. Yeah. I kind of don't like it because it implies that beam line is doing nothing, where it's actually quite an important beam line.
Yeah, I just like that it's the photon that's like hanging out, seeing what's going to happen, right?
The signal beam hits the sample and then hits a detector, and the idler beam doesn't hit anything and then hits the detector. The whole system only says I have a photon if in the exact same picosecond it detects the signal photon and the idler photon.
Yeah, so I had a question about this.
Yeah.
Is that for this to work, it's required that the beam paths be exactly the same length?
I don't think so.
Okay. So then how do you know that the photons, like what prescribes that the photons that reach the detector, that the entangled photons that reach the detector will reach the detector at the same time?
Oh, I see what you're saying. Sure. I guess they don't have to reach them at the same time, but if there is a time difference, you have to know the time difference.
Okay, so you do have to know very precisely the length of the beam path.
Yeah.
But it doesn't have to be equal.
Yeah.
Okay.
But I think that's easily calibratable.
Oh, yeah.
Right?
Yeah, I mean, with just normal light, you could do that, right?
Anyways, the point is that they can use this cheat to reduce their signal to noise, because they can essentially say, I'm going to reject every single photon that does not have this double incident. And that's actually a kind of cool
this
ability.
Coincidence is what they were very...
That's kind of a cool ability, because it means that they can reject a lot of stuff. So you could be simultaneously imaging your sample with a different microscope, and this microscope wouldn't care, because it doesn't care about any photons that it didn't entangle, create, hit the sample with, and double detect.
Yeah.
Which is pretty cool.
Okay, I have like a stupid question.
Yeah.
Why aren't all photons entangled? Is it just that these photons we know are entangled? Because this is just like the way that you generate this biphoton.
What do you mean?
Is it goes into a crystal and becomes 2 photons of lower energy. So like is any photon that's lower energy?
I don't think that's how this works.
To create the biphoton?
Well, they're not creating a biphoton here.
Yeah, they are. They're creating hyper-entangled photon pairs.
I think that's different from a biphoton. Like, isn't that what you told me at the very beginning? The biphoton is this tremendous trick where you had big photon, you split it into, you had little photon, you split it into two big photons, and then you get little photon back at the end or something like this. Anyways, the biphoton is
No, but
one.
they're using, okay, I mean, my understanding is limited.
Should that be the title of this episode? My understanding is limited.
But I think that this SPDC process, which is
Spontaneous parametric down conversion, type 1.
is the way that you create the two lower energy photons.
Here they don't talk about creating two lower energy photons.
What do you mean? How are they entangling the photons?
We use
It's
two beta barium borate nonlinear crystals with perpendicularly aligned optical axes to produce hyperentangled photon pairs.
Okay, but then they say SBDC beam. So they're using this SBDC.
Sure, but why do you think that's the same trick as a biphoton?
What's the difference between a biphoton and two entangled photons?
So these are two entangled photons, which are at the same energy, they're at the same polarization, and they're at the same spatial mode, right? But there's nothing about these two photons like starting at one energy and splitting into double energies and coming back to one energy. Like the biphoton trick.
I really think this is the same thing.
Let's see. Let me try to find it. Because they compare to their other, because it's the same group that did the biphoton. Okay, this is going to be hard to slice together because I'm going to say a statement and then we're going to have to think for a long time.
Okay.
But so we probably just put a cut there because we just sat for like 3 minutes thinking really hard about something. But I want to read from page 3, bottom left. Okay. The 38% resolution enhancement achieved through virtual spatial filtering of the multi-mode SPDC beam with the entanglement pinhole as described here and theoretically analyzed in note S2 is fundamentally distinct from the twofold super resolution imaging at the Heisenberg limit demonstrated in 10,32. The latter relies on the principle that the equivalent wavelength of the entangled biphotons is half that of the SPDC photons. So that is why I say this is not the biphoton trick.
Okay, well, I am confused then.
Because the biphotons was a very mind-messy trick that I still don't understand. And I think I understand most of the tricks here, which is why I say this. It's the biphoton, you somehow, let me see if I can get this right. You start with a photon that has an energy.
Has an energy and a wavelength.
And a wavelength. That photon splits into two photons, one which hits the sample and one which doesn't hit the sample. No, because this is not right from the get-go. You start with two photons that have an energy and a wavelength. They're entangled and they somehow mysteriously create a so-called biphoton, which has a 2 energy and therefore half the wavelength. Because energy is proportional to 1 over wavelength for those who are listening. So you hit the sample with only one photon.
So you have to hit it with only half the energy because the other energy is with that other photon.
Yeah. And so you don't hurt your sample as much, but you still, for some reason, get the half wavelength resolution.
Yeah.
That's the magic biphoton trick.
Yeah.
Here, you're hitting, you have 2 photons.
They are entangled, but they're not entangled in this. So biphoton is like a special way of entangling photons?
Yeah, I think biphoton, you should think of it as you have one big photon and it's been split into 2. Their energies are half of the one big photon, but their wavelength is the wavelength of the original big photon. Whereas these entangled photons, you have 2 photons and they're just locked together. They have an energy and a wavelength corresponding to their energy. So they have the correct wavelength for their energy, but they're locked together in sync on energy, polarization, and spatial mode. Now, how you create the biphoton or what the biphoton even is, I have no idea. But that's not what this paper is about.
Okay, so the thing that has confused me is that they are both somehow generated through this SBDC method.
Yes.
And so I don't understand what the difference is in
But I think the SBDC is kind of like, it's one thing kind of down the line that many things have to be true. And so are they both created via barium borate nonlinear crystals? Are they both created through type 1 SPDC processes, or is there, because that implies a type 2 SPDC process. But I think you are going to have to take that these are entangled photons.
I am hearing, yes, I believe you that this sentence that you just read says that this is not a biphoton.
Yeah.
I am confused about how you generate specifically a biphoton versus just two entangled photons. And then I get to the question of just like, my understanding of how you're creating these entangled photons is an energy drop.
Yeah.
Because that's what SPDC essentially stands for, right? What does it stand for?
Spontaneous parametric down conversion.
Yeah. And so then are any photons that are lower energy, like there's an entangled buddy out there and we just don't know what buddy it is?
No, so to be an entangled photon, you had to be created by an event that requires that you preserve certain symmetries, right?
Okay.
So like the like classical thing is you have like some quantum event where you create an electron and a positron. Because they've been pair produced, one must have equal and opposite like spin and things.
Okay, but something that's just like a fluorescent protein that gets excited and then is decaying, that's not, there's no...
Yeah, you just got one photon from that,
yeah.
right? And even if you got two photons from that, because there was like an electric transition, there's all sorts of places that the symmetries can be resolved.
Yeah.
You specifically get entanglement where the only way to resolve the symmetry is that your two particles have to be equal and opposite.
Okay.
That's what you get entanglement from.
Great.
And so one of the tricks here that they use to get like kind of very shitty confocality, so they do a bunch of weird tricks here. The biggest trick in my mind is they go in with a pretty dirty beam. They go in with a not very focused beam. They're just trying to hit the sample with light. And they say, look, the way that we're going to get a nice image out of this dirty beam is we're going to reject everything that scatters by only we're just going to have a very, very tiny idler beam detector.
Yeah.
So only things that perfectly went straight in this. So they're basically going in with a flashlight, right? And they're trying to do laser imaging with a flashlight. And they get away with it because of this second path.
This entangled pinhole.
Entangled pinhole, which I was really unhappy about the naming for this for a while. And the more I understand it, the more I'm okay with this statement. That like the pinhole is on the detection side of the idler beam. And the pinhole, quote unquote, is just the fact that the detector is very narrow. Fine.
Yeah. And
fine.
It's what's allowing you to reject all the not.
But it does mean that like, this is not exactly confocal microscopy that they're doing, which I guess isn't a surprise now that I finally got it in my mind that this is really bright field microscopy. Like I said, they're going in with a flashlight. They're kind of literally going in with a flashlight. And so the reason why I say is then they say, look, not only can we get better signal to noise ratio and we can create this kind of artificial confocality, but they say, because we know the polarization completely, basically they say we can put polarizers in the idler's way rather than in the main sample's way. And so we can figure out the idler photon's polarization state completely. We get the flux from the signal photon. We get the polarization state entirely from the idler photon. And this is why I say, going back to this polarized fluorescence light sheet microscope paper that we covered a few weeks ago, we once again are getting label-free understanding of the birefringence properties of the sample that you're imaging. However, in episode 5, that was a confocal method because it only worked on fluorescent proteins. So you got this 3D structure. Here, it's not even that it's out of focus. You literally are getting the optical properties of the photon flying through the entire sample. So you get a pretty two-dimensional image. Anyway, we started talking about that. I wanted to get back to it.
Well, so they do in figure 3A, right? They have this Z stack, and that's where I was scrolling to earlier in the episode when you were talking about this is not confocal. Is they do a Z stack through this very sparse carbon nanotubes image, and what they are showing here is different focal planes. So when you have a sparse image, like you're getting the optical properties of the whole agarose pad, but that's most of the signal is coming from the carbon nanotubes, and you're getting your spatial resolution the best in the correct focal plane.
Yeah. And so I guess what I was surprised by is like there is some focusing here, but I think when you're considering how does your polarization property of your photon change, like here you can do deconvolution, you can figure out what your sample might have looked like three-dimensionally a little bit.
Yep.
In the birefringence, I don't think you get
Right.
anything.
And so this is like a limitation that we've talked about a lot of these birefringence measurements is that they seem to be kind of inherently 2D. Like how would you possibly make a confocal birefringence measurement? And so this was a label-free confocal birefringence measurement.
Label-free. And that's the key part because, right, like what we did in episode 5, which I didn't understand for a while, is that we had a fluorescence, a fluorophore-based way of doing this. One thing that you could do here, right, is like they're only not confocally imaging because they go in with this flashlight rather than a proper laser scanning beam. And they go in with the flashlight because they say, look, the reason why this doesn't work is traditionally in order to get enough counts to make an image, you have to sit there and integrate for a month. You have to just shine the laser on the sample for a month to get enough quantum events. Here, we're going to go in with just a huge flashlight so that we have an excess of photons, and the imaging is only going to take like 10 hours. And the image still takes like 10 hours to make, so it's still incredibly slow. But the thing that they've lost by doing that is the three-dimensionality. So they wanted to get an image on a reasonable timescale. You could have gotten a three-dimensional image, and they talk about this a little bit. Maybe you could start to try to recapture a 3D image or something more interesting or a better timescale if you had much better sources.
So much better light sources, much better lasers.
Yeah. These problems there's a quote is, these problems could be resolved in the future by using more powerful quantum sources generated with metalens arrays or gated quantum dots in optical microcavities. A strong entangled photon source with high coincidence rates could substantially improve the imaging speed, and the SPDC beam could be filtered into a single spatial mode for diffraction-limited imaging while maintaining a sufficient signal-to-noise ratio, which is extremely challenging to accomplish using existing quantum sources.
Okay, cool. I mean, that's pretty exciting to me because that is at least an avenue by which you could get label-free birefringence measurements.
But we're still talking about it where we are now with this in their table. They say it takes 1 second per resolvable pixel. So if you want to take a 200 pixel by 200 pixel image, that's 40,000 seconds, which is going to be something like around the line of 10,000 minutes, which is going to be forever, right?
Yes, I understand that we're not
week-long imaging.
Yeah, that there is a limit, but that in theory it is possible. I hadn't seen a solution using classical microscopy. For getting 3D label free.
Yeah, and I mean this whole all the things you could think you can do if you're allowed to do this entangled pair measurement process, which I deeply don't understand. Like this, I kind of get. The biphoton really messes with me. Where it's
I mean, this I think is why we were so fascinated by the first paper and why we have continued to think about it for so many years. Is we should go back and do the biphoton paper. I thought this would be a continuation of it, but this is a different thing. Yeah, it's like a real life, when you take quantum mechanics, your quantum mechanics course as an undergrad, you're like, wow, is this really how the world works? This seems crazy. Like the math works, but is this how the world works? And this is, as people who do microscopy all the time, to solve a problem that we've been running into for the past, 50 years using quantum mechanics is
I think that's why I like the squeezed light thing so much, because that's like a very clear problem that I know that's a very clear solution that works using undergraduate level knowledge of quantum mechanics. That's all like peachy. Then we hit this biphoton. And I'm like, I don't think I learned that in graduate quantum mechanics. I don't think that vibes with my understanding of anything. So
yeah, but the fact that it works, right? I mean, assuming that, wouldn't it be cool to build this microscope and see the 2x resolution difference by having entangled photons?
Can I say some bad things about this paper since we are so critical of biology papers?
Yeah, let's say some bad things.
None of the figures' titles are sentences. So figure 1 is just experimental setup and signal SSN signal retrieval. And while the setup is vaguely readable, B, C, D, E, F mean nothing. I stared at them for a while.
Oh yeah, I didn't stare at them very long. I was like, histograms.
A lot of these graphs are not very useful. None of the captions are titles. And one thing that's annoying me is, I don't know how they would do it, but I want a video because we're not going to get a video for this YouTube upload. I'm going to have to go take a video of just something
No, I took a video of us assembling the light sheet last week.
Great.
So I think we can use that.
Oh, let's use that. Sounds good. Other things
Yeah.
that I don't like, there's no math in the main paper.
Yeah, I didn't like that. I understand it's science advances. It's supposed to be for a general audience. But general, like all this go see note S2 or S5 for the
Yeah.
actual advancement was kind of annoying.
We got to get math back in papers. It's incredibly difficult to understand what's going on if you're like hula hooping your way out of showing any math. I don't agree with it for the biology papers, but like I could see where people are coming from. This is a paper about quantum imaging. Give me my math. I had a really difficult time with they kept comparing their technique of quantum imaging with classical imaging. I had a really hard time with this because what they mean by classical isn't like, oh, if we use like a scanning confocal microscope. What they mean is literally if you put your hand in the way of the idler beam, that's what they're comparing to. If their own microscope just ruin the photon entanglement, but their own microscope is just a flashlight,
I thought it
entangled
was
flashlight, where you get or you get some pinhole effect by the entangled photon. If you ruin that, you're literally just comparing to what the image would look like if you imaged something with a flashlight. That's not a good comparison.
Oh, what do you like? What else would you compare to? I thought that was the only way to compare.
I want it compared to a scanning confocal microscope.
But like, yeah, so much could be different.
Sure. It's just like they're like, oh,
they
it's
could be
better.
they could be using
38% better than classical. It's 38% better because you stop putting your hand in the way of the optical path.
Yeah, but I think they're just saying that this optical path works, that this pinhole, this entangled pinhole
that's true.
works,
That's
right?
true. But I just like, if that's the criteria, any microscope that I build, I can say it's 100% better than the Bez fuckery microscope where I just put my hand in front of the laser.
I think that they're doing something a little
100% improvement from when, we just...
when we take out the disc.
That's a better analogy. That this feels to me like
But
saying,
I
I've
think that
created this spinning disc,
Yeah.
and I'm going to compare it to just completely removing the
No,
disc.
but I like Yokogawa. I mean, I don't know if they published a paper, but in whatever document that they have about Yokogawa, I'm sure that they say, look, we are 40% better than if you use a different disc.
Sure. Yeah.
Right. And like, I think it's the same thing here.
No, it's not. This would be saying, look, we are 300% better than if you just don't use any disc at all. Or I think this is very close to saying, look, this is 40% better than if you just put your arm in front of half of the disc.
Okay. I mean, I guess like you're arguing that they should have put a disc somewhere in there, like had the same light path, put a normal disc in the
Or
incident beam.
It should be compared to some like actually used classical imaging technique.
I just think that doesn't matter.
What do you mean doesn't matter? This is the podcast.
Well, I just think we're going around in circles. That I was going to say, like, I was just going to say the same thing again. That
another difficulty that I have, and I have this with
apples
all the
to
quantum
oranges.
imaging thing, is like the quantum people are not biology people. This is like my constant problem of people who build microscopes really at the fundamental level of you're building a brand new thing are never people who like really have much experience taking images of samples and trying to do science. And so they're like,
having a zebrafish in an agarose block kind of vertical is not your ideal sample prep.
It's not. But a lot of what they often say are the problems with quantum mechanics is like, hey, our technique is better because other techniques necessitate the integration of high precision translational stages, thereby extending the imaging duration substantially. They also say, like, here's one that they do that's crazy. They say our technique directly measures coincidence using single photon detection, while most wide field quantum imaging techniques use electron multiplying charge coupling devices, EMCCDs, just cameras, right? Which do not have a high frame rate to measure the arrival time of a single photon, and therefore require a large number of frames to retrieve the coincidence statistically. I'm sure that they're right about that it's better to not have to move a stage, and it's better that the EMCCD is technically slower than the single photon detection device. But these don't vibe with what I actually need to take a biology measurement. And like the number one thing I would say to all the people who are building quantum imaging microscopes is go find a system that develops really slowly. Like go find a chameleon embryo and image the chameleon embryo or something, right? Like biology doesn't have to be fast. You don't have to go image something fast if you're not building a technique that's fast. Don't compete with that. Go image something really slow. Biology is also really good at being really slow. And if the field of view isn't working for you, find a biology system that has the field of view you need. You're trying to prove that your system is usable. Go find the ideal case to use it, and then you can start to play these games.
Yeah, I think that and this is a problem that we kind of discovered in our PhDs, is that the finding a biological or experimental system for a microscope is not trivial, right? You like build this, you imagine and you build this beautiful microscope, and then you need something to study with it. And
yeah, it's an interesting trap.
And so, one way to approach the trap is to imagine things you want to study and then develop the solutions. But I think the people who write these papers are very much like imagining the solutions and
then trying to find what fits this.
But
they don't have enough experience to find what fits it.
And so they publish this paper, and hopefully somebody else finds the...
Yeah, dude, if I could build this, I would build this. This seems so freaking cool.
How much, how expensive is did you look up how much entangler
when you said,
be?
what's the difference? How do you create a photon? I was like, what way I was going to go about trying to explain to you is I went and tried to find a list of what I would have to buy from Thor Labs to build this.
Cool.
But I have a couple paragraphs I'm going to throw at you that I did not understand.
Okay.
And I'm going to see if you understood them.
Good luck.
Page 6, under quantitative quantum birefringence imaging through polarization entanglement. They say, whereas most existing quantum imaging techniques rely on the spatial entanglement of SPDC photon pairs, quantum imaging modalities use polarization entanglement, such as quantum holography. What's quantum holography? Is that what this guy made in the Dojik lab after we left, or that's just normal holography?
That was just normal holography.
So what's quantum holography in this context?
I don't know. I highlighted 10 as something to read, but I didn't read it.
All right, going on. The polarization entanglement of the SPDC photon pairs in our system can be characterized by Bell's test. I assume you don't know what that is?
No, again, highlighted it, but don't know what it is.
I mean, it's like Bell's, are we talking classical locality versus
I don't know.
non-locality?
We didn't even have to go to a different paper, but we did have to go to note S4.
Yeah, I'm not going to note S4. Put it in the paper.
Or
it's the editors,
figure
it's the
S10.
Journals, can you please, your internet first, behave like it. Give us our goddamn, just give me the information. Stop hiding the information everywhere. Okay. Our system shows a substantial violation of the Clauser-Horn-Shimoni-Holt inequality.
Yeah, so I also...
Saying it out loud is great.
Yeah.
Clauser-Horn-Shimoni-Holt inequality. Do you know what that is?
I don't, but I think you can infer from the rest of the sentence.
Oh, really?
Demonstrating strong polarization entanglement. So it's an inequality that, is like a conjugate variable thing.
Okay, next question. Ghost birefringence quantification. Could you figure out what they meant by ghost birefringence quantification? They use it a couple times on page 7.
Well, so they were talking about this ghost imaging for a while.
Ghost imaging, I think I understand, but that's a totally different technique. Ghost imaging gives you confocal images. In fact, they say ICE fundamentally differs from ghost imaging, whereas ICE is ghost birefringence quantification.
I don't see the sentence you're talking about, so it's hard
the
for me to
very
follow.
first sentence on page 7. Right under figure 6.
Well, did you know what the Mueller matrix components would be?
No, but that I felt I actually got from context.
Okay.
Is that the full birefringence matrix is called the Mueller matrix, right? And then
ghost. So this is just what you just said. This ghost birefringence quantification is because you're measuring it on the idler beam instead of on the
I don't know if that's right. The
beam.
reason why I don't know if it's right is that ghost imaging in quantum mechanics is a very different technique. Where I think the way that ghost imaging works is you have your idler path and you have your sample path.
Yeah.
Behind your sample path, you just have a giant bucket that just says, any light that I get.
Yeah. Are you entangled with this friend?
Yeah.
Yeah.
So it's just a counter.
Yeah.
And then your idler path is recording really carefully where is the position of that photon that I got. And from that, you can build a confocal image of a fluorescence sample. That's ghost imaging. So ghost birefringence, well, I guess it's not ghost birefringence imaging, it's ghost birefringence quantification.
But I feels like anything with the word ghost just means that what you are measuring is on the idler side.
Anything with the word ghost, what you're measuring. Okay. So ghost imaging, you're really measuring the image of the idler photon position.
So you can send, and the rest of the sentence is ICE can be used in remote sensing applications.
What does that mean?
So that means that you have your quantum entanglement source, and you send one of your photons like way off to some place where all you can put in is this second detector, and then in your where you can actually have an optics table where you have your analyzer and polarizers, that's your idler path.
Is that true? So you're
ghost.
saying that I don't need to be able to get a detector on the other side of my sample? No, because they say we're the source.
I do still think you need a detector
I don't think
on the
this
other
is
side
the correct
of the samples.
interpretation of the sentence. ICE can be used in remote sensing applications where the source is too far to be controlled in real time. And that's why I'm why do I care where the source, the thing that's creating the entangled photons is too far away to be controlled? What's that situation? We're getting entangled photons from the sun?
Yeah, I'm confused again. I think you're right that my interpretation was incorrect, but I'm not going to get a real-time interpretation that is more correct.
Yeah, I can't really imagine. Oh, actually, I went to it just now. I went to figure S12 in supplementary. You're never going to guess what it is.
Oh, yeah?
I'll give you a clue. I was very close.
Oh, yeah?
It's not the sun. It's a satellite emitting polarized entangled photon pairs.
Okay.
I have no idea. What are they on about? Oh my God. With ICE, the full birefringence properties of a remote object, the remote object being a satellite in space, can be quantified by locally changing the polarization states of the photons without interacting with the source and the object. I'm not going to be imaging zebrafish from a satellite.
No, but so this, I think this is for a totally different application where you're just I wonder where photons go. And there's
paper
photons.
was titled Quantum Imaging of Biological Organisms, not some shit about. Can you get a satellite? Can we just have a great laser source, a 48 laser in space, and you just rent time and you just put your sample out in the yard, and you're at 3 p.m. I'm gonna get a beautiful image of my sample because the satellite's just gonna shoot a laser down. This is a truly ludicrous figure.
I don't know how you're seeing these figures. They're not in the PDF.
No, they're in the supplementary material. They also have a sentence at the very, very top, first sentence of page 8, which I think is moderately important, and maybe we should read a paper about this, in which they say, third, the entanglement pinhole is a virtual pinhole that filters SPDC modes in coincidence detection. In practice, all the SPDC photons in the signal arm still transmit through the object, which undergoes an illumination photon flux higher than the 2-photon coincidence rate used for quantum imaging. What do they mean by 2-photon coincidence rate used for quantum imaging? Page 8. She's just shaking her head. I believe on the regulation podcast, they would say that you've gone nonverbal.
Illumination 2-photon coincidence rate. So I this is all jargon to me. Even coincidence is still kind of jargony.
The reason why I ask is I was reading that there was some controversy over a proposed quantum entanglement technique in which you would entangle the photons in such a way that you'd be able to excite the 2-photon effect for 2-photon imaging, not by going in with a tremendous flux of photons, but by going in with 2 photons that were already pre-described to have the super tight timing to make the 2-photon. Because normally you get 2-photon by just using so many photons that you're 2 of these photons have got to show up at the same time. But you might be able to do some clever quantum entanglement trick to ensure the 2 photons show up at the same time. And then you have 2-photon imaging just using 2 photons at a time, which would be revolutionary, right? And so I wonder if that has anything to do with this sentence or if this sentence is completely unrelated.
Yeah, I felt I don't understand this sentence, but my interpretation of these 2-photon coincidence rate is of the 2 entangled photons arriving at the detector.
I think that's probably the correct interpretation.
Whenever they talk about coincidence elsewhere in the paper, they're talking about this coincidence detection, which is the whole thing that gives them this resolution in this pinhole.
Yeah. So it's super cool work out at Caltech. I didn't know about any of this kind of stuff when I was an undergrad or a graduate student. It's wild to hear about these days. Do you have any more comments about the paper?
I mean, are we going to go through, I guess we should go through our questions.
Oh, yeah. That's true.
So
what did you think is intellectually beautiful about the paper?
Yeah, I mean, what I think is intellectually beautiful is that you can use quantum mechanics to improve imaging. When I first read about it, I thought that's crazy talk. And to see it actually be employed is very beautiful. If you could have one thing added to the paper, what would it be?
I think I would have had them go get some thin sample that's alive and evolve very slowly. Like go get some moss or something, right? And make a video out of that.
Yeah. Well, so one thing I wonder is, do these quantum sources, I guess they don't get used up is what I understand.
What do you mean used up? No, you're not like burning a fire or something.
I'm just wondering if it's like expensive to run this thing for a long time.
You pay for electricity, but yeah.
Okay, and then do we want to do the ASIA levels?
Sure, ASIA for the levels. I think we should kill the specifically scientifically what was this paper about thing and just talk about, I don't know.
Well, I think we should shorten what this paper was about. I think it's nice to say, maybe not for ASIA though. Maybe we separate it and we say, okay, at the end, we'll just summarize the paper in 2 sentences for our listeners.
All right, so the summary, this paper was about using quantum entanglement where you have one photon go off and interact with the sample, and you have another photon that you mess with to learn its polarization, and that lets you do some polarization microscopy tricks that you couldn't normally do. It's really cool. It's really beautiful. It's not quite ready for prime time. I think it takes them like days to take a single image, but it's really cool stuff.
Yeah.
And then
broadly in the world, why did you care about this paper, Bez?
Yeah. So for ASIA, again, we've harped on this before, but your father really cared about using imaging for diagnostics, for helping people's lives, for understanding what's going on and what's going wrong for people who have problems or for pets who have problems. And so thinking about diagnostics is a lot of thinking about new technologies of how can you image something better? How can you image it deeper? How can you see what's happening? And these quantum tricks mostly feel like they're a dead end, but there is this hope that like, I don't understand the rules there. And so then I start to hope, are there ways to really cheat? Like if I can make a 2-photon where I don't have to put in an incredible flux of photons, I can diagnose your cancer through microscopy, through something your father knows, right? This is weird because like half the audience would have to ASIA, but I'm talking to ASIA right now. That if I can do that, I could do 3-photon microscopy. I could go a centimeter deep into your skin. Once we start to get into these real like quantum rules, it's not so clear to me where the limits of measurement are anymore. And so I start to become very hopeful about what we could do. And so I start to like read it.
Great. Okay.
And so with that, it's another episode. Thank you for making it to the end of this journal club with us. I wonder if a single person will ever hear these words right now.
Yeah, I wonder.
This is a rough paper to get through. I loved reading it, but I think it's a rough paper to listen if you haven't taken all these stupid courses in your life.
Yeah. But I also think it's one I think that will age well in that people who stumble across this paper are going to look for resources to help them understand it.
Yeah.
And hopefully this will be a resource. Some people struggling along.
Thank you so much for listening. Go vote for episode 15. Nobody's voted. I don't know where to put a poll, right? Blue Sky doesn't let you put polls up. LinkedIn has like a 10-character limit. YouTube, nobody uses YouTube polls, right? I've never seen a YouTube poll that I clicked on. Nobody interacts with the Patreon, which has it best set up to do the poll there. So
okay, send us carrier pigeons of what.
Yeah, just text us. Text us which paper you want to
comment on the YouTube
15.
video. Whatever way you are currently viewing or listening to this, you can
if you successfully contact us via carrier pigeon with an episode that we should do, regardless of whether it was part of the original vote or how many people have voted against you, we will cover your paper just because of the feat of reaching us via carrier pigeon.
Okay, and with that,
thanks for listening.
Bye.